Go to the next speaker now. Professor Aljabri. The title of his talk is Spectral Analysis of Ice Shelf Vibrations. And Professor Aljabri, you can share your screen.
Can you hear me? Hello? Yeah.
Yes. You please share your screen.
Is it visible? My screen?
Yes, you are visible.
Okay.
Your screen is visible.
Should I start now?
Sure.
Hello, everyone. My name is Rehab Aljabri. I am a PhD student at the University of Newcastle under supervision of Professor Mike Milan. And today I'm going to talk about spectral analysis of ice shelf vibrations, which is part of my PhD topic. We are going through the outline, research motivation, background information, and the case of clamp-free ice shelf. First of all, let us see what is the ice shelf. Ice shelves are vast floating plates connected to ice sheet and glaciers that exist along the Antarctic coastline and other Arctic region. They cover an area bigger than 1.5 million kilometers square, occupying 75% of Antarctic coastline. And now we're going to see why is it important to study ice shelf vibrations? Well, because various climate projections illustrate the rapid melting of ice shelves around Antarctica and provide evidence that the melting of ice shelf in the region has increased dramatically in recent years. Also, Antarctic ice loss has contributed significantly to rising sea level up to 1 meter by the year 2100. Also, seismic instruments detect ocean swells effect on the Rosie's ice shelf in Antarctica, causing it to vibrate. That's why studying the vibration of ice shelf may help us understand the risk of such a catastrophe. We can see here a picture of ice falling off an ice shelf in Antarctic, and this may lead to raising the sea level. Now, the mathematical background for ice shelf. The vibration of ice shelf was first mathematically studied by Holdsworth and Glenn, who proposed that ice vibrate to the ocean swells and lead to iceberg calving from ice tongue. Also, the majority of previous studies have investigated and used a mathematical model of ice shelf that are analogous to the beam theory. And this theory is used for finding stress and deflection and is based on the early work of Ray, Holdsworth, and Klein. And in our work today, we will study the vibration of an ice shelf floating in shallow water using the same method, which is linear beam theory. And this work will be similar to Serjonko and Milan, which calculate the normal vibration mode analytically and have shown that ice shelf vibrates only if their vibration matches the eigenfrequency of the shelf, which may lead to iceberg calving. We can see here the mathematical problem and the schematic diagram of our problem. And as I mentioned before, we will be following Serjonko and Milan. We can see here, we're going to assume there is an ice shelf clamped from one end and free from the other. It's clamped when x equals 0 and free when x equals L. The plate will be, we will model the plate as the linear beam theory. Underneath the plate or the ice, there is a cavity, and the water in the cavity is shallow, and the water will be incompressible, and the motion will be irrotational, and the water also inviscid. That's why we're gonna describe it by potential velocity phi. And the water in the cavity also shallow. Here we can see, as I mentioned, it's clamped from here and free from the other hand. Because it's clamped from here, there is no deflection and no slope, and because it's free from the other side, will be the bending will vanish and the shear force will vanish. And as Serjonko and Milan, they assumed here underneath the ice in the fluid, they assume there is no flux condition, and we're gonna follow the same assumption. Here we can see the equation for the ice shelf, which is the linear beam theory. D is the flexural rigidity, and eta is the vertical displacement of the lower case of the ice, because we said here, we say there is a draft approximation, so we're going to ignore the draft. That's why the lower case of the ice will be the ice. It's not the surface of the water anymore. So here eta is the lower surface of the ice. So rho sub I here, the density of the ice. H here is the thickness of the ice, and rho sub W is the density of the water, and G is the acceleration due to the gravity, and H capital here is the depth of the cavity. Okay, so as I mentioned, under the assumption of linear water theory, we're gonna assume this is potential velocity, and the potential satisfy the linear shallow water equation, which is the Stoker equation. And following Sir John Cohn-Milne, there is no flux condition. And here is our equation, which is the linear beam theory, and I already described every element inside. We're gonna assume here our thickness of the ice will be 300 meter, and the depth of the cavity will be 100 meter. The length of the ice will be 40 kilometers. And here is our boundary condition. The variable eta from this equation will be eliminated. But if we want to eliminate the variable eta, we're going to use the shallow water equation. So that's why we're going to take the derivative with respect to t to this equation and substitute it inside the shallow water equation. Eventually, we will end up with an equation containing only phi. So now, after that, we're going to use the non-dimensional variable. So we're going to divide every x with the characteristic length and the TC, which is the characteristic time. So this is similar to Fox and Milne. And here is our LC and TC. And from now on, all our equation will be in a dimensional version. And here is the variable LC, and here is TC. And our domain now in non-dimensional variable will be from 0 to 31. Because we divide, it was 40 kilometers, but we divide it with LC. Now the non-dimensional version of equation 5, which is this one, will be this equation, and M is the single, this equation depends on the singular parameter M, and typically M is much less than 1, and this is, in our case, this is what M equal. So we will solve it like time harmonic solution. We're going to use the separation of variable, and then after we solving like this, this is a typical eigenvalue problem. Omega here is the angular frequency. So it's really an easy equation to solve like this. Now we're going to use the boundary condition for phi, because this is the potential velocity. And as we mentioned here, this one and this one is the no flux condition. And for the rest of the boundary condition, we just raise all the boundary condition here to the second derivative using the shallow water equation. That's why we end up with this boundary condition, which is 6 boundary condition satisfying our equation. Now the general solution will be take this form. And we can see here K is the root K of the characteristic polynomial. And this is an eigenvalue problem. So now we're gonna enforcing the boundary condition, which is 11 and 12 on the solution, and we will end up with 6 linear equation, a matrix of 6 linear equation as we see it here. So in order to avoid the trivial solution here, we need the determinant to be equal 0, or another way we can say we need the matrix A to be singular. So that's why we're going to search inside the matrix A to find the angular frequency that satisfies our assumption or our solution. So we solve numerically, use the minimum of the absolute value of the eigenvalue of A. So, and then searching for the value of omega, and that make this function 0. Once we look at the angular frequency omega n for the matrix A, so our matrix will be singular, and then we can find this coefficient, which is C1, C2, C3. And after that, we find it. and the table one, and I will show it to you now. And this table actually it's matched the previous work of Mylan. We can see here, we find this is the non-dimensional angular frequency, and here is the dimensional time. And we notice here, this is the longest period, the first one here. And we notice here, the time will be decreasing while the angular frequency will be increasing when n gets higher. Okay. Now, the associated mode shape for the potential is given from the zero eigenvector C. So here, this is the mode shape equation. And after we finding it, now we plot to find what is the first mode shape. This is the first mode shape for the potential, and this is the second mode shape, third mode shape, and so on. Now, the main aim for our work is to use this mode to simulate vibration in the time domain. So the potential phi x and t expand in terms of the mode as this. So this is the general solution for the potential velocity. And b in here depend on the initial value, and d in here depend on the initial derivative of phi. Now, we made an assumption that this is our initial condition. So we made an assumption this is the initial condition, phi x and 0 equal f of x, and the first derivative will be x0. So in this case, this term gonna vanish because the first derivative equals 0. We will end up with thus only this solution. So we need to search for the coefficient Bn, and now, for finding the coefficient Bn, we're gonna like multiplying both sides of equation 18 by xm, then integrating the result to obtain this formula. And then we will approximate the integral by numerical quadratic as this. And xi here are an evenly spaced point between 0 and L. And wi here is a weighted function, and we choose it to be trapezoidal rule here. And then we introduce the following matrix. So we changed we transfer everything to the matrix term. So here is our matrix X, and here is our vector F, and WB, and so on. So this is how we find our coefficient Bn. Now, it is important to note for function f of x here, our function, in the beginning, we made this assumption. So our function f of x, there is some restriction in this function. So not all functions satisfy our solution. So we're gonna take the integral from 0 to L for equation 1, which is the shallow water equation. And then after we find the integral, this part gonna vanish because basically we made an assumption that no flux condition. So here will be 0. This term will be the integral from 0 to L to be equal 0. And here is our solution for eta. We know that this is the mode shape, and here, as we did for the potential, as we make a separation of variable. And now, if we're gonna take the derivative for this, we will end up with integral from 0 to L, mode shape for the vertical displacement to be 0. So the function f of x must be satisfy this equation, which is 24, which means the area under the curve for the plate must be 0. So for choosing the function f of x for that vertical displacement, we must follow the condition, which is here, 24. And for phi, we can represent it by any function, but we need the angular frequency is 0, the first one to be 0, which is the 0, 1. And that will lead to x0 of x equal 1. Therefore, the final solution now will become like this. And as I mentioned, f of x for phi, we can represent it by any function. And we did a simulation for the solution. We chose f of x as a Gaussian function, and I will show you now what is our solution will behave. Here is the red one is our function f of x. We choose it as a Gaussian function, and the blue one is how our solution will be like behave, and we change everything to be in dimensional unit. So here x in kilometer and everything in dimensional unit. Now, for finding the mood shape for the vertical displacement eta, we will use equation 1, which is the shallow water equation. We're just gonna take the second derivative for the potential to find the mood shape for the plate or the ice shelf. So we end up with this equation, which is the mood shape equation. And here the mood shape for the plates. We can see this is the first mood shape, and here's the second one, third one, and so on. And we can notice here the mood shape match the boundary condition because we said it's clamped free. So here it's clamped and free from the other side. For the vertical displacement, the general solution will be given like this. And we can see here Gn depend on the initial position, and Sn here will depend on the initial velocity. And we made an assumption this is our initial condition. So eta x and 0 equal f of x, and the first derivative in terms of time will be 0. So that means this part gonna vanish, and we will search for the solution here in this part only. So for finding the coefficient Gn, we will do the same things as we did in the potential. We will write it as a matrix and then find what Gn equal. And here is our final solution. And for finding the function f of x that satisfy eta, we need to be to have a function that the area under the curve equals 0, as I mentioned before. So we did simulate the solution. Here is our function f of x, and here is our solution. And we notice here the solution matched the boundary condition, which is clamped from here and free from the other side. And the solution in dimensional term or dimensional unit. And this is my reference. Thank you for listening.
Thank you. Any question from the audience? Susam?
Yeah. Rehab, you have explained well, but you mentioned your ice thickness is 300 meter. So which model you have used for ice plate?
Linear beam theory. We use linear beam theory, which is in here.
But that is generally used for thin plate model. This Euler-Bernoulli beam equation.
Yep.
But here your thickness of ice is 300 meter.
Yep. Our thickness of the ice, we choose it to be 300 meter.
Okay.
But I think
what's the tell Susam what the length of the ice is? How long was that?
I think the length is 40 kilometers, so 300 meter
Okay.
can be thin ice.
Okay, got it. Okay, thank you. Yeah.
I have one question. That is, you are fixing that at x is equal to 0. This is you are taking eta is equal to 0.
The initial condition, you mean?
Yeah. But on the other end, you are saying it is a free. If I look at your result, last but one page.
You mean my initial condition here?
Yes. What made you physically, how you can say that it is fixed? Is it that one end is fixed first?
We choose the function that satisfy the potential velocity like this.
Okay.
Yeah.
No, I mean to say that your one of the edge is fixed, other edge is free. So how you fix that edge in a physical situation?
I can choose any function to satisfy the potential. So any function will work in my.
No. I mean to say your deflection is one end it is fixed. The ice sheet is fixed at one end, other end it is free.
Yep, correct. Yes.
Okay, so what made you to fix that one end? What is the physical criteria for this? Could you get my question?
You mean I need to find the function that sets?
No. I'm telling what is the criteria that you are fixing that at the one end it is fixed, other end it is free.
Yes.
Normally, so how physically it is possible?
Well, the clamped end because it connected to the ice, the free one because it's toward the seaward.
Okay, and the other end?
It's clamped to the ice or grounded ice.
No, how you clamp it? That's what I'm asking. Because this is an assumption, or it is in physical it is possible. Okay, maybe
I
you
think
look.
I can there's a lot of debate about that, but it's got to have about what that boundary condition should be, but it's got to connect to the other ice shelf somehow.
Okay.
And we sort of know that the Antarctic ice shelf's not moved. The ice that's not on water, that's on the land, is stuck.
Okay. Okay. If any more questions? If not,
Rehab, you could show us that picture of the
okay.
motion of the shelf again. I think this one here.
Yeah.
I'm not seeing any motion here. I don't know why. Yeah, there we go.
No,
It's very
that first end we have taken fixed at 0, x is equal to 0. How this was fixed?
it's clamped. There's a solid ice sheet like
Okay,
Rehab
so you are
showed
seeing
you.
that
Yeah.
it is clamped.
Yeah. It's kind of glued on to that
Okay.
other ice shelf is the idea.
Okay, maybe in the shoreline it is clamped and similar clamp is okay.
Yeah.
And can we add to this problem? Can we take the lateral compressive force and look at whether any changes comes in the due to the compression? Professor Melan.
I think you could include that. I'm not sure it's I mean, given that it's floating out in the ocean, you can't imagine too much compression, but yeah, you could examine that.
Okay.
You can see in that figure how complicated the motion of the ice shelf is. Like these ice shelves are vibrating like that. Nobody's people have measured only particular points, but the whole ice shelf will be vibrating. It'll be more complicated as it's two-dimensional. That picture that Rehab showed, you're going to show that again, Rehab, just play it again. That it just shows you the kind of very weird way it's moving. It's sort of almost because of the sixth order equation, kind of a strange. It looks very odd, doesn't it? The way it's moving, it's almost random, but it's completely deterministic.
Okay. Okay. Thank you.